student felt they needed some basic information.
Where's your presentation?
Or we felt it, but it's also. I mean, I hope everybody will find something. So I hope you might find student work. Hopefully there'll be something for everybody. But it's really this issue of I mean, it goes a little bit into data analysis. What are we trying to do? What are we trying to say? I might choose. But feel free to interrupt, ask questions, whatever, in the middle of the discussion. And is this the only other thing they have this morning?
Yeah.
So we have plenty of time.
Yeah, we can either do epic, we have time, or we'll do epic.
Yeah, we have
First
everything.
thing
We have,
epic.
yeah, we have everything. So statistics is a discipline that's concerned with study of probability, study of uncertainty, and decision making in face of uncertainty. So that's it's about collecting, organizing, analyzing, interpreting data. So we have different kind of data that in our field as well. There's what's called nominal data, categories that are not ordered, like your phytoplankton that are over there. It's not one that's more than the other. We have ordinal data, but it's not, I mean, they're ordered, but they're not, it's not necessarily objective, like things like pain level or, and then there's most of what we collect, which is scale data. Things that have units and we can differentiate them together. Why do we need statistics, you may ask? So it helps provide answer for questions such as what's the concentration of phytoplankton on the dock right now, and how it can compare to something before, or how it's likely to be tomorrow based on what we measured today. So what's the likelihood that tomorrow will be twice as much phytoplankton or there'll be a harmful algal bloom, given everything we measured in past years in front of you. And one thing that talks to me when we do, often we use stats just to reduce our data. Just not have to, when we talk about our data, not have to talk about every wavelength and every spectrum we collect, but a salient description of all the data we collected that's sufficient to explain, to show what we got. Just like when you showed us your data from the experiment, you didn't show us every spectrum and talk about every study, you talked about the average and how much variability there was. There's a point about whether statistics make the points. Statistics never proves anything. So put it in your head, you're not proving anything. You can talk about likelihood. And this is a point that I really, really like, because particularly with young scientists, they really love to show the mathematical prowess by bringing very, the latest and greatest statistical thing that goes like this and does this, and they downloaded the package in R that's really amazing. And I love this point because if you need fancy statistics to make a point, usually it means that your point is weak. If it's not obvious, it's probably not very strong. It might be there, and it might be that you need a special technique to see it in the cloud of data, but it's not a very strong point. So, for example, we measure a sample which is only part of the population we want. Then we describe it with statistics, our sample. And then it tells us something about the population. Who is there, how much. So there's really some basic statistical moments, you all know them. There's mean, there's variance, standard deviation. What is this n that we have here typically? What do you want this n to be? This n here. Well, basically, are all measurements equal? Particularly when it comes to measurements, understanding of variance. What do you think? Or standard error. Standard error is a standard error of the mean. Actually tells you that the more measurement you do, the more certainty you have about the value of the mean. population. So, let's go back to your chlorophyll exercise, where each of you is taking from the same bottle, another bottle, and then runs it. Is this the same as if each of you went to the field and took a sample at a different time? What's the difference? Right? Exactly. Independence of samples. So the assumption here is that the samples are sufficiently separate that they give that it's a new sample from the population. So when you run water through the ACS, or when you do the ACS, even worse, when you do the ACS in mode where it's a strength of double the mode, so the same water is stuck there all the time, you're not reducing the uncertainty. The more measurements you're making of the same water. And when the water flows through, you have to make sure that it flows fast enough if you want to use its native 4 Hertz measurement. If you want to assume each one of those is different, the water has to be replaced in your flow tube sufficiently fast, and there's also mixing in the tube. So to be independent, you have to think about, is it truly independent? Is each sample independent of the previous? That I can use them as independent samples. And if not, how do I scale? How do I reduce it to what I estimate to be? And another thing, often people want recipes. What's the right statistics to use for this data? For me, often it's what's reasonable. It's not what's right, it's what's reasonable. And there's no one recipe that's the right way to approach data with statistics. There's what gives me information about that makes sense to me about a distribution. And I'll show you some examples soon about where. So this is one of the classic things that we talk about when we talk about uncertainties. You probably, I don't know how many of you are familiar with this diagram. I assume most of you. But the point is that often, so that this on one axis here we talk about precision, and on the other we talk about accuracy. So the worst obviously is when you have low precision and low accuracy. But from my perspective, this is even worse. And this is worse because you think that because you have a scale in the lab that can measure 0.001, it's great. But you've not calibrated. And you might be completely off the right value, but you're deluded to think that you're getting great data simply because you get 3 points after the decimal. And this happened to us. In 2001, we deployed the float, and the float did not come back. One in the ocean. First float with fluorescence at that stage. Went down. This was the most anal person I've ever seen, who was responsible for ballasting and everything. Came back and said, after strong analysis, he went through his notebook, everything is written in his notebook, and said, it's my fault. The scale was not calibrated in the last few days and it's sufficient. At that time, we were off by 2 grams the last week. That changed sufficiently for it. And thank God, again, riser had sufficiently floated, another float was found, and then another sensor was found, and we were able to deploy it floated for 3 years to give us beautiful data. Right? This is the most dangerous part in the world because you don't know how bad you are. And you're deluded to think I'm doing great. The biases, and the other thing is biases don't get reduced the more measurements you make. You cannot decrease the standard error of the mean the more measurements you make. You're still off. But you think that, oh, I'm making all these independent measurements, everything is going down, my mean is better characterized. But it's a mean that might have an offset. So what I fear at night is of biases. Biases is where I fear the most. Yeah, so the standard error doesn't get reduced. So the other thing is, most often we do mean and standard deviation, and we don't think about the fact that they have inherently a meaning to us because distribution under it is normal. So we know that the mean for normal population, half of the population is above, half is below, that within one standard deviation of 68% of the data. That's true for this. It's not true for different distributions. So this one is an example of the height of male population in inches. But here we might have a population like this. This is 8 and 10. And suddenly, this is a non-normal probability distribution, but suddenly the mean is not going to mean the same as it did for the previous population, or the standard deviation. We're not going to get 68% of our, or 95% within two standard deviation of the mean. So one of the first things you can do when you get data, plot the histogram of this distribution. It's very easy to do. And what you find with bioptical data, typically it's the closest parametric, meaning a distribution that you can assign a function to. The closest it is typically to log normal, not to a normal. So when you log the values of the data, suddenly you get a normal. So there's other statistics. You don't have to, and you've all used them. You don't have to assume that there's normal distribution. You can tell people what the median of the data is, what the percentile is. You can tell them that you know that within 16 and 84%, you're going to get 68% of the data. If you describe a percentile, you don't have to go, and it will equal plus minus standard deviation in a case of a normal distribution. So that's the deviation estimate would be that. But there's one problem that we found when we use medians compared to means is that if you do it for spectra, it tends to be quite jagged. There's something about the mean that smooths data. So if you still want to do that, sometimes what you may want to do is remove outliers. And the way you do it is you don't remove them, you just not use them in calculation. Say I'm going to keep, for the purpose of calculation of the mean, I'm going to take all the data between my 95th percentile and my 5th percentile. And that's what's going to be. And this is what Guillaume is implementing in time analysis. He wants the smoothing property of mean, but he doesn't want the outlier to go into the normal context. And we do it by finding some criteria about which percentile you use to calculate. The data, we keep data, but we don't use it because we believe that a lot of those are due, for example, to bubbles running through your system or things like that should not influence our data. Another thing that you'll find in the literature, which I really like, is robust statistics, and now it's implemented in MATLAB. You can do robust regression, and those tend to be regressions that don't take outliers into account. In this case, if you let these points that are here and here affect your line is going to be completely skewed compared to what by eye you feel is the relationship between the data. This seems to be the relationship, but you're going to get this. So some people will throw away these data, but you don't have to throw it out. You can use these robust regressions, leave those in so everybody sees that, the all kind of measurements that you don't necessarily understand, but they're there, but they're not going to affect the line that you're plotting through, and you might propagate after. Totally honest with what you measure, and these actually might be the points that will be your next discovery. There might be something about them, these are the harmful monospecies, something that is throwing my average relationship between a band ratio and some biochemical variable out, but they're still extremely valuable data points. And maybe I'll spend some time investigating why are they different. If you throw them, then you never have them to ask that point. And there are rare special cases in the ocean. We have monospecific blooms where certain assumptions about size distribution, about a whole variety of things go out the window. And we don't want to miss those cases for the average because they don't deal with our expectation. So be very careful about, from my perspective, data is sacred. You never throw it. You might decide you're going to remove it from your analysis, but always keep it and always ask yourself whether there's something there to find. Otherwise, you'll never find something new. You'll never find something new if you force your data to agree with what the field is already decided. So the new information is in these things. It might be new issues about the methodology we use. It might be new things about what's in the water, but that's where really. So here's an example. This is I showed you the picture of me with diving with the practice on track in the Bahamas. So this is data we collected at that time. This is with Ron, and we had a coral reef and sand next to it. And all I did is just dive with a hose at different depths to see, whether there's differences. And one of the things you'll see is that the closer you are to the bottom, this is 10 centimeter, 50 centimeter, 2 meter, the more spikes there are, and the more, and I quantified as a difference between the mean and the median. You can see the distribution here, but the underlying distribution here of the measurement, this is beam attenuation, total beam attenuation, so CPG relative to water. Values both, the values here are not very different from each other on the scale, but what's different is these large particles that you find near the bottom, or large rare particle that might be zooplankton, that might be something else. The other thing is we also see, so this is above the reef. But this is, what you see is that you get the spike above the reef and not above the sand. So it provides you information, this variability, about what's happening on the reef that is not happening here on the sand. Like the organisms, there are these organisms. The other thing we saw here is that as we go closer to the reef, CDOM increase. When we did measurement in other figures in this paper, we get, the closer we get to the reef, the more CDOM we find. And the closer we get to the reef, actually we could notice a decrease in total particle, which made sense for us in terms of filtration of particle and production of CDOM. It's not as evident here, but it's in the paper. There is a slight decrease. Okay. So how can statistical theory answer a research question? It allows us to derive relationships between variable. For example, the blooms were nutrients or plentiful, or a week after they were. Contrast conditions, diatomic versus dioxide combination associated with freshwater input. It also allows us to assign uncertainties, and we'll get there soon. So I'll show you some stuff that Charlotte has analyzed. She's not here. But this is from a paper she published last year, and where she took all the distribution available of KD from radiometers on flows. So she took the full order of distribution out of the data set, downloaded the radiometry data, and then looked at how it's distributed. But she also looked at how it compares to distribution that have been used to derive algorithm. And this is what you have here. So this is 380, there's no algorithm, it's in the UV. This is 412. So again, this is the underlying distribution in the data set. And this is the distribution in the IOCCG data set that has been used to do algorithm with. You see Nomad here, the red one is Nomad. And then the coast look is these ones, the green. And what you observe is that the distribution that went into deriving algorithm is very different than the distribution in the ocean. So these were used to do global algorithms, yet that don't represent these distributions in terms of the histogram of probability. Let's just start. Afterwards, we'll talk also about spatial distribution. And this one is 490. So you see they're all biased high, and indeed what she finds is that there's a difference. There's a bias in the algorithm that she derives compared to the other global algorithm. And the other thing that's really cool about this data set, at the time when she did it, there were already 41,000 profiles of her geometry. She's amazing compared to what you had in these data sets. And then once you reduce it to match up with satellite, she was down to 10,000, 11,000 match up with satellite that you could work with to do algorithms. We're starting to get a lot of data, maybe not enough, but much more than there was there to derive algorithms with. And this is the distribution. So sadly, when you look at where they come from, half of them come from Mediterranean. And then the rest, a lot in the Southern Ocean, and then you see a little bit in the equatorial region, quite a lot in the North Atlantic. And most of the NOMAD data set is from here, from the North Atlantic only. So this data set is more geographically representative, but it is biased towards certain waters. And what you see in color here is the biomes as defined in a certain paper from Galen McKinley, I think your name is, from Colombia, where they divided the ocean into 19 biomes. That's the background. So what Charlotte did in order to have an algorithm that's not biased, what do you think? How would you, if you knew that this is how the data is distributed, how would you remove the geographic bias from it? What would you do to remove a geographic bias? What do you think? What?
Calibrate to the difference.
So how would you calibrate to the area? So yes, so you're right. I have this area, and how would I use that area in order to reduce its influence on the total algorithm? Remove a point of this, but how do you choose how to remove? And representing in what sense? The number of points or the area. So what you want is to represent all areas of the ocean equally. So you're going to come up with a weight for each point here, and this is what she did. She weighted them both by the area that it represents in terms of biogeochemical properties, but inversely to the number of measurements in that bio. Because if you have a lot of measurements, you weigh them less, or you randomly sample within them, so it's representative similarly of the area that they represent. But you still see that there's huge areas, despite as good as this data set is, where there's not even a single float that has a real. And when you deal with global algorithm, they might or not work. Particularly if they are fully empirical algorithms. They're not based on rate transfer, or they're not based on some knowledge of what should be the relationship. If you use something that's based on radiative transfer and it works everywhere else, you say, well, radiative transfer is physical theory, it's likely to work in any water. But if it's purely one that is empirical, you wonder, well, the phytoplanktons here are different than phytoplankton somewhere else. Maybe it's not going to work. So these are things to think about. So there's been, thank God, a lot of movement in but also information we have. So the idea with Bayesian statistics is we're not coming to this problem empty-handed. There's relationship between parameters, and we might be able to leverage information from what we know, so that we can get better estimates. So the Bayesian statistic is looking at questions like, what is the likelihood that a species X is blooming given location, date, and ocean color and temperature? So I'm using past data, all these, to help inform the future. Because there's certain probabilities between what we see. And one of the problems I've found with the way we often do inversion from space is we use no information. Just seeing color. About getting functional species from space. They find Procolococcus in areas of the ocean where we know they don't grow. So if you inform your algorithm about that knowledge, you might then use a different phytoplankton spectrum that would be more to the region you're in. So this is extremely powerful because we know that temperature puts huge constraints on phytoplankton and on living things in the ocean. Let's use that also in our algorithm if we want to improve that, where it's relevant. But it requires knowledge of conditional probabilities. What's likely that a certain species will be in these temperatures? So now suddenly we're bringing back life history into our science about the biology. So there's an unrelated but a super story that I read, that I got acquainted about it in a book called The Case of the Dog in Magnum. I don't know if you read it. It's a super book to read. But it's this fun problem that is very hard to wrap your head around. But I find it useful. So you're now in a game show, television game show. Okay? And many of you may have encountered. The host tells you there's three doors. And two of them there's a goat, and one of those is a car. And if you get the car, it's yours. Okay? You start by selecting a certain door that you will open. Eventually, you're allowed to change that. If you're telling the host, whatever, the game show host, I think I'm going to use this door. And then he will open one of these two, because he knows what's behind it. It has a goat. One of these two will have a goat because we have two goats in the car. So for sure one of them will have it. He would say, okay, we have a goat here. And that you now are allowed to change the door you're going to pick to this one. You don't have to change, but you're allowed to change. And the question is, will you change your pick of the door? Does the fact that he tells you that which one of these two has a goat changes the probabilities that this one will have a car more than this one? How many of you think that, how many of you would change doors, knowing that which one of these two has a goat? That they've never seen this problem. How many of you will not change your choice because you think it doesn't matter? It's still 50-50. So all of you abstain. Yeah, I would have said exactly that. And it turns out it makes a difference. The fact that you know, and I'm not going to do it now in front of you, but go online. It's a beautiful problem. But this is exactly where Bayesian statistics comes in. This is information you did not have before. And that information tells you about these two, something that you didn't know before, that increases the probability that this one will have a car. Yes, ma'am.
Isn't this true only if the host has knowledge of what's happening?
Yeah. I mean,
So that's an assumption that you made.
That's an assumption.
Yes.
Yeah. But it tells you that he opens one and has a goat. But just that act changes the probability that this one will have a car compared to this. And it's completely unintuitive, but it's beautiful. And you can go online, look for this. Google solver. You have solvers, you have places where you can click and see for yourself that if you do it enough time, this one will have a third compared to this one, likely of getting that. Which is, yeah, it's mind-boggling. But this is the power of knowledge, where you bring more information in. This is the power of Bayesian statistics in essence, is that you're bringing knowledge into helping you solve a problem that you did not have before. Okay, so now we look at relationship between variables. So we can calculate a correlation coefficient. We've seen them. Or we can do it with order statistics. So if the data, if we don't want to use, this is a parametric, we can use non-parametric by ordering our two data sets from smaller to biggest and just do the same number with order. A correlation between, is the biggest like the biggest. And here is a great example that I love. In all these distribution of points have exactly the same, they would regress to exactly the same line, and they have the same mean and standard deviation of all the variables that you see. Note that there's an outlier here. And this is why when you write a paper and all you give me is this, I'm going to say this is not enough. Because it's not, you can see how different what you expected. Oh, it's probably something like this. And this is also why it's so good to provide the data before that you do it with. This is the most, of course, the most frightening one.
I see all the time.
This is the case you see all the time.
No,
See, yeah.
when you're looking at like air as a function of depth
Mhm.
between acoustics and LiDAR,
Uh-huh.
like no will only give you the mean.
Yeah.
Or if you
Yeah.
never see the plot,
Yeah.
you know, plot it, so-
Yeah. And you can see that in this case, by eye, you're going to put a different line. And one of the biggest problems of R for me is it's totally affected by the dynamic range. You have a big dynamic range in your data, R is better. But it says nothing about my ability to predict one variable from the other one. I might be able to predict just as well with a much lower R. But there's just not a lot of dynamic range in my data. We often laugh about it, but we're very lucky to have a field where dynamic range is, this is our second beautiful relationship. If we just, take a transit from the coast out, we stay in front of the dock, much less dynamic range. But with the tide, hopefully enough to get great R. But we're not improving our prediction necessarily by having these orders. So now we'll talk a little bit about regression model. So when we're trying to predict something from another, and now often it has to do from this perspective that there's a dependent and independent variable. It's probably well, that's our independent, and then there's one that depends on it because we're trying to infer causality, which we cannot. But then think about what it means. I mean, in terms of an absorption spectrum, the independent would be a wavelength, absorption would be a dependent when we plot them, or time series of scatter. But often what we're really interested in is the parameter like, for example, chlorophyll versus size. And what do you think is different between these and these ones? As the two. What's the independent and dependent when you do a regression of chlorophyll versus size? We might assume that the size is independent because we put it on the X, but what's very different here is that our knowledge of wavelength or our knowledge of time is pretty good. In this case, we might have just as big an error in size as we have in chlorophyll. And so when we regress them against each other, we don't necessarily want to assume that one is known perfectly and only minimize in one direction. When you do regressions, the type 1 regression, you minimize only in one direction, not in both. And these are type 1 regression. So you assume you're trying to minimize in only one direction. And you can account also for, just so you know, you can account, each point has a different error. You can account when you do regressions. You weight them such that they don't weigh as much. But here I'm assuming all of them have the same error. Now, these are, what do I have here? I have a model, linear model, very simple, and then I have a cost function. And this cost function is minimized to get this A and this B. This is what we minimize. So we're looking at all the A's and B's with all our data points, y, I, and x, I, that will give us the smallest value of this function. For the cost. Just so you know how it works. This is what Excel does. Excel, this is exactly what's done. Although this case you can solve another. There's one case, this you can get. But if you have errors in both x and y, now you're changing the way you're doing it. Now I have an error here and an error here. This is not anymore the same as this. And you're going to get a different line to take into account. And it's not going to be simply the inverse of the line you're getting. And that's actually a fun exercise to do. Is to plot y versus x, do a line, x versus y, do a line, and see how different they are. Is one just the inverse of the other? No, it's not, typically, because you're minimizing the different direction. Then we have this thing called coefficient of determination, which has to do with the mean square error, etc. You'll see people say that it explains the variance. It does not reveal cause and effect. Nothing does. It's strongly affected by the dynamic range. The bigger the dynamic range, the bigger, more variance is explained, because variance is also affected by the dynamic range. But there's a great book that my father used to have when I was a kid in his house, so which I enjoyed, which is How to Lie with Statistics. So how people use statistics with an agenda to push it. And you want to be very careful about that. You want essentially what you want to see is the distribution. Don't just show me statistics, show me the data, show me stuff, but show me in a way that I can evaluate. Don't give me every data point in the table, that makes no sense, but show me so I can indeed get a sense of how it works. So there is the type 2 approach is the one that takes into account errors in both, and there's different ways to do it. One of which is that it's simply you end up with a slope that's the geometric mean of the two slopes, and with a given uncertainty. But if you've never done type 2, check it out. And there's codes from Embari that are great. You can find them online and run them and read about the assumptions. They link to papers in statistics where it is derived. But it's very useful. And again, if I see a paper from you coming, where you only need type 1, I'm going to ask you to do that. But you know that there's uncertainty. But in any case, the same approach, approach can be assigned to any model, and that takes into account uncertainties in all variables involved. We often like to smooth data because data has noise, and noise might affect our relationship in ways we might not want. For example, like we talked about outlier. Some of it might be instrumental, some might be in the environment, just like I showed you from the reef example, where we have large, big particles. But sometimes the noise is where the signal is. And we talked about it a little bit with respect to the work that Nathan Briggs did. So Nathan Briggs basically developed a method, and there's some paper pointing from Schifrin pointing to prior, to use this in the noise as a way to get information about the average size of the particle causing the. And if you know something about the amount of water you look, you can also do concentration. So this is an example of noise in the least. This is the diameter of the least, but these are the spikes in beam attenuation, the spike in BBP, and also the spike in the beam attenuation of the least. So it's 3 instruments here. And then he uses these spikes to predict the size, and you regress it against the size in the least. And this is an experiment just like I showed you in the lab. This is an aggregation experiment in the lab. I think he analyzed the same data that Wayne, it's straight the data that Wayne analyzed several years before. And there's an equation there that has to do with how much the sample volume and input from me theory, something about the independence of the measurements that ends up giving you an area, the average area associated with the measurement from which you derive a diameter. But it's amazing how well it agrees with the least in this.
Roll over some certain size fractions.
Oh, that's what we, I guess, I mean, that's what we, this is the log 10. So this is 100 micron, this is 10 micron. So it's a relatively large size. But yeah, you see that it's not fitting as well in this part where there's very little noise. So that could be the reason. And in this part, which I'm sure we'll discuss in a bit for why we think there might be an issue there. But this is the beauty here is it's all based on, sorry, on spikes. I'm looking at spikes in a signal. And we have many assets that might have spikes in them that we're not taking into account. So currently in inline analysis, we don't take any advantage of the spikes. This could provide maybe information about the bubbles more than anything else, because many of our spikes are bubbles, but it could be information that. So this is the rare large particles that are in your assembly, or in this case, these aggregates that are sinking, that are in low enough concentration that they're not part of the continuum. They appear as high. If there were many of them, then you'd see them all the time, and they're not going to be rare in our measurement. So we model data because it allows us to condense or summarize data by fitting into a simple model. It's convenient for us. We can think about a CDOM spectra. In essence, we take 84 wavelengths of an HCF and condense it to 2 parameters, which seem to fit really well the data. So we don't have to talk about that. Same we do with beam attenuation when we fit it to a power loss spectrum. Although now we see with the 84 that there's features near the chlorophyll peak that have information. So we want to look at those two in terms of adding information. And so we can fit, and the way we fit data, a certain model into data, is also by defining a cost function or merit function, doing our measurement minus this model, and finding these 2 parameters that give us the best fit to everything. That's how we do it. And this could be squared, but it doesn't have to be squared. This is least square minimization, but it could be absolute value. Some people even use square root. And for me, the Bible on all this topic is called Numerical Recipes. The book I bought when I started with science, and it's a Bible that sits on my shelf. My students have it on their shelf. It's everything you want to know about fitting and how data analysis. There's super text there, and I love to read. They have codes, but what I love is the text in between, and it's all about what makes sense and robustness. It's a logical explanation. It's not a mathematical one, and it's written by engineers. For nonlinear models, you need to provide an initial guess of these parameters. For example, if you use the function fmin search in MATLAB, but as we said before, you can use an absolute value as your minimization. It doesn't have to be the root mean square. The problem with the root mean square is that points that are further away weigh more, or because you square the difference as you minimize it. So this might be much more robust. But this is not continuous. Again, the reason people use least square is because initially, before we had computers, you could derive analytically the fit of a line that will have minimization of the square. But now with computers, we can put whatever we want in the cost function. That makes sense. I'm not going to go through these stacks, but you have it as a slide. But it's really a nice description as to why we care about having uncertainties, and we always should have uncertainties, and we should always think about all the errors in our system that can contribute to an uncertainty. So there's several formulations on how you do it. When you have a simple equation relating to variables, so now we're thinking about 2 variables, x and y, and a third variable such that q is a function of these 2 variables. Okay, I have x that has a mean value plus minus delta x. uncertainty. And the fractional uncertainty will be dx over the mean. So implying that this is kind of the value. A small number of a small number of relationships would serve you well. So, for example, if your equation is an addition or a difference, and if the two are non-correlated, x and y are non-correlated, then the uncertainty in the sum or the differences can be calculated from this formula. Similarly, if you have a fractional relationship or multiplication, the fractional uncertainty can get from this formula. And often you can use these and propagate them through quite big equations, not always. This is for a power equation, etc. So how do you get from the uncertainties in x and y into the uncertainty in the sum, multiplication, etc. There's a great book by Taylor about error analysis where all this is found, and where you see a train going through a station.
It's called Introduction to Error
Yeah,
Analysis.
and all this is developed there really nicely. So this is one way to propagate error. But often we have models that are not simple equations. And in those cases, for example, in the Sidon fit, you want to know the error in the S, in the exponent. How would you go about that? Or outer light, we want to know what's the uncertainty in outer light. How an uncertainty in my AC input, ACS input affects reflectance. We have something like this. We have a black box where we have an input and an output, and we want to know the uncertainties in the output. We know them in the input because we measure them in the field. We think we know the uncertainty in the calibration. And then we put it in a black box and we get it out. And this is where Monte Carlo come in very useful. And Meg will do an exercise with you on exactly that next week. So we use what's called bootstrap method or Monte Carlo method, where we vary each input variable by itself within its uncertainty. So we take a random number and we say, okay, I have a distribution. I have a distribution around it. I have a variable. I have my ACS spectra. Let's say I have one of the input would be, just as an example, AP 440. And I know it within delta. So now I'm gonna, if I assume it's normal, I can now choose a value. This would be, if this is standard deviation, this would be plus minus delta here. And I can throw a dice or a random number that will tell me each time a different value from here. And then I do it for each wavelength or the BB or each input. And then I run hydrolyte with all of those, if I assume they're uncorrelated, picked in an uncorrelated fashion, and then I see how it varies my output. It is the easiest method to do error propagation. As long as the inputs are present, because you don't have to think about the function, you don't need to think about how do I do it, you don't have to go through these formulas. And now with computer power we have, it's very easy to do those. Just vary our inputs within the uncertainties, plug it in, and see how it varies out. And this could be anything from you could use it for an AI, you can use it in many kinds of approaches. So, for example, the way I did it first was to try and estimate what's the uncertainty in this S. So I feed a line. I want to do the uncertainty in S. How do I do it? So what I did is you're adding uncertainties in this was with an AC9. So for each wavelength, I would put an uncertainty within, based on, for example, the standard deviation in my lab measurements, and then see how this would change. You do it 10,000 times, 20,000, you can add, you can double each time the number until it's steady, and then you get an uncertainty for the S. You're going to get a mean value and distribution around it. So now you can put error bars on your S, you can put on your amplitude fit as well. Just by varying your inputs based on reasonable assumption. But again, what's reasonable is what you think are the uncertainties. And if you choose them too conservatively, you're going to get very small variability in these. And if you're, so you have to think about what is it that I'm choosing? Is it going to be the standard deviation? Is it going to be the difference between multiple independent samples I'm taking from the field? You have to think about what is it, what's an independent value that I can then get an S that represent the state of the waters in front of my dock. So this is a paper that was mentioned by Jeremy yesterday, where they look at estimating pixel level uncertainties in reflectance for Moody's. And what's really cool is they did both this approach of derivative that leads you to this, both this approach that's based on taking derivative of the equations and the Monte Carlo approach, and both converge really nicely. So give you confidence that you're doing things correctly, and you describe how things went around it. But basically, it's looking at the dependency of your, in this case, reflectance or water leaving radiates on every input to the model, every input that goes into the model, and its own uncertainties. That's how you calculate this things. Another paper that came out relatively recently had to do with just a showcase of an algorithm to get backscattering, and it's a line-height algorithm. It uses 3 wavelengths to a red, a blue, and a green wavelength to derive backscattering. But also, how do I put error bars on it in a way that's realistic and based on what we know at this time? I'm not going to go into the detail, but I suggest you look at it if you're interested in errors. And then finally, there's a whole IRCCG report that was edited by Muller, who did most of the work in that takes about how you do uncertainties in our science. So this is an example I just took from what they consider as uncertainties that are important. So uncertainties in input data, like top of the atmosphere data, ancillary data, all those have uncertainties, like what we saw, what's needed to derive reflectance. And then uncertainty associated with models and algorithms, like what do we assume the atmosphere to look like, cloud, ice, and land, sea surface, so land would be the adjacency effect, issues with sea surface, how we propagate those, optical properties of the water constitution, how variable are they, vertical distribution of water constituents. So if we have vertical distribution, which mostly we ignore, how much problem can it be, effects of bottom, IOP and AOP, and effects of bidirectional reflectance. So that's the fact that you're not watching in zenith, you're watching in different angles relative to the sun and viewing angle. And just going through what is likely to contribute. So if you're not sure about what uncertainty should I assign, that could be a good place for you to look. And also what we know about uncertainties. So it's not just enough to do uncertainties, you want to validate those as well. So one of the discussions we now have in place is we all are supposed to develop algorithms for that uncertainty. And they want us not only to validate the algorithm database, but also that the uncertainties are reasonable. How do you validate uncertainties? How do you go about that? And that will, for example, will have to be that if your uncertainties are supposed to encompass a certain percent of the data, when you measure in the field, indeed, the amount of data, 68%, 95 confidence interval, whatever it is, they should work within those specs. And remember, 95% is not a huge constraint. With a 95% confidence interval, 1 in 20 would be outside. So just the fact that randomly you do the measurement and it's outside doesn't mean that the algorithm is garbage. Didn't pretend to work 99% of the cases or 99.9, only 95. So, and they talk about phytoplankton groups and other things. So it's worthwhile looking at. We talked a little bit about information content. You saw there was a mention of the paper that Calvi, where he took ACS data and looked at how many degrees of freedom were within that group. But you can ask yourself, we talked about the fact that dissolved spectrum, despite the fact that I have 84 wavelength, I can probably fit it really well. So in essence, if I have two wavelengths, good, I do not have an estimate of uncertainty. I don't need, for C down, I can use an AC4, AC5, and AC84. Question is for particular spectra, how many wavelengths do you need? So at least globally, on average, using PCA, probably 4 or 5 degrees of freedom. It will not encompass all the cases. It's going to encompass well the average cases. If you have again a very special bloom, a very special situation, you might need those extra wavelengths. So how do you go about figuring it out? People have done, so you do it with, for example, things like PCAs or empirical octagonal function. It does depend on your uncertainties. So your level of confidence depends on uncertainties, and those need to be taken into account. And so lately, Cal did a similar analysis, but this one to reflectance. So he took 191 hyperspectral reflectances and did the same analysis as or similar analysis to the one he did for the absorption, putting a threshold uncertainty in the measure that is based on the measure. The smaller the uncertainty, the more you can squeeze out. And what he found is that if he uses the hyperspectral, which is this one, there's about as many degrees of freedom as you find in motives, on average for these data. And these data come from these points. Again, they're heavy on the Mediterranean because Tara had a whole mission with a lot of scientists. And this is where it comes from. So it's not representative of everywhere. But with these data, it finds that motives and the hyperspectral data have about the same. And that, that's to be debated. And then it looks at something else, which is really cool. It takes C waves 1 degree by 1 degree monthly climatologies, and then look at how many degrees of freedom are in place. And what he finds is that there really is about 2. Well, if you look at the information that you get from all the products, POC, chlorophyll, PIC, C-Phyto, size distribution, before it that, there might be even, this is the significant threshold, that this black curve, based on uncertainty. So even less so if you basically saying that all these products are essentially one product. But then in reflectance, there's more information that we're not tapping out. For, again, 1 by 1 monthly climatologists of series, I think for 10 years. So in the mean state of the ocean, there's not a lot of independent information in the products we're currently producing. But there is more information there that currently we're not tapping. We don't know what it is. But there's something there that we could tap that is in the color that we're not using now. So the current product extremely well correlated. There's not independent, and additional information is available that we don't use. So to summarize, use statistics logically. If you don't know the underlying distribution, use non-parametric stats. Okay, it's easy. Everybody understand what they are. They don't prove anything statistic, but can give you a sense of the likelihood of a hypothesis about relationships. When you derive relationships, think where they are applicable. So think about where in the globe are they likely to work, particularly if you're trying to produce a global algorithm that was not tested in most of the globe. And I strongly encourage you to study information content, hypothesis testing, and Bayesian methods, because these are relatively new in our field, and you're likely to find things that other people have not. And also be careful about how to use them, because there's been a whole controversy around p-values and how they're misunderstood and misused. So when you use, you have a lot of people that love to do statistics and put p-values. Just be careful about what you infer from them about rejection and hypothesis or no hypothesis or that. There's a lot of literature on that. And that's what I have here. Thank you. I'm sure my colleague has much more to add to that session. First, students ask whatever question you like to ask them.
You like the scientific scale,
What?
the scale.
Yeah.
So on the bottom, what was the black line with this, that is the.
On the bottom, yeah, this is the significant threshold. This one. So if you're below, it's considered not to be.
Based on the. What are the parameters?
No, no, it has to do with the uncertainties in the measurements and propagating uncertainties in products, et cetera. But you have to go. Whatever I'll say is probably wrong. So. So how many independent? So when you do a PCA or a big orthogonal function, you start with how much of the variance can I explain with one behavior. So the first behavior would be one that will be a linear combination of these. And it seems that you can explain, within your uncertainties, you can explain what you're seeing with only one combination of these particles. Again, within this, the fact that it's a monthly 1 by 1 degrees climatology, and then you take all the reflectances that you get in each pixel. It might be that if you looked at daily and you looked at each, removing clouds and whatever, that you find that there's more significance and more variability, because whenever you're doing averages, you're moving things tremendously. But this is the kind of stuff that is often used by people. Yes.
Can you explain why the significant threshold is so different for these two PCA?
Yes, this is simply based on what you think is the uncertainty of the reflectance measuring with a hyperprobe beyond above. So this is what determined here how well, because the first mode will explain here about 70% of the variance, and then the second mode will explain an additional, et cetera, et cetera. So each mode explains less and less, and then we start getting into the low side, where the additional modes are below your ability. Yes.
I'm just curious, is there anything where is this the right way to think about information content? It's linear, dimensionality reduction.
Yeah.
I don't know a better way, necessarily.
Yeah, you're absolutely right. This is one way to do it. So when we did the absorption one, we actually, the first one was nonlinear. It was a chlorophyll. One of the approaches we did was to use a nonlinear, which was remove a chlorophyll correlating. In this case, would be a shape. And it didn't yield more information, but it yielded things that had spectra that made sense to us. We talked about it in the previous lecture. But the interesting thing is that another group published within 2 months of us a paper finding, they use the same methods, but using a completely different data set and finding the same numbers of degrees of freedom in the perspective. So at least it was consistent across data sets. It's not just the fact that we have these 191 points that is reduced with the weight. But this is not a representative data set again. And so the way I think about it is not that hyperspectral is not useful and will not have a lot of information for us. But to get more information, we have to be extremely creative. To identify the region of the ocean that are outliers, they're different than this. This is a representative of the mean, and the mean is relatively stable and it looks in a certain way that we're used to it. Then there are going to be special cases. They're going to be the monospecific blooms. They're going to be maybe the upwelling regions where things are not going to look like this, and they're not included in this, where there will be information. So it's not that we don't need that information, but we need to be very intentional in how we approach these data. To take full advantage of the access. And by the way, this is not new. When I arrived to RSU in 1997, I talked to Jim Mueller at the time, and he I think he did his PhD there, or he was associated with technical physics. And he basically told me that you don't need hyperspectral to do it. You can explain 98% of the variability of chlorophyll. That's an average statement. In every 1 point or given time, there's more information. You just have to intentionally find things. And that may require, methods, different methods by which or bringing more information. How do we bring with space more information? We use the polarimeters. We use SST. We use other things we know about the environment. We use where we are on the globe and what day of the year. Are we in the spring or in the fall? That's information that is affecting what is likely to be in the water. The more constraints we should bring that are independent of our measurement, the more likely we are to obtain useful information. Okay, this is not a big. I'm often wrong. Yes.
What are the numbers in between brackets and
These numbers,
Yeah.
how much of the variance is explained by the first, second, third, and fourth?